Hello world! In today's video, we'll understand pulse width modulation using the timer functionality in MSP430. Do check the previous video on the basics of timer in compare mode on my channel to get a better grasp of this one. Alright, so let's first understand what do we mean by PWM. Now in previous video, we were blinking the LED using the up mode of timer, which means that the LED was on for 50% of the time and off for the rest of the 50%. Now what if I want the pulse to be on for say longer duration of time? Let's say 75% of the time it should be on. That means 25% of the time it should be off. Or maybe it should be on for say 25% of the time. That is, I'm decreasing the time period for which it is on, and off for 75% of the time. This means that I want to modulate the width of the pulse, and that is what is our pulse width modulation. And by the way, the percentage of the time that we are discussing over here for which the pulse is on, that is T on, is specified in terms of another fancy term which is called as duty cycle. So now let's look at the PWM logic in MSP430. That is, how do you get a pulse width modulated signal in MSP430? So first we'll use TACCR0 register. Now from the previous video we know that we use CCR0 in up mode. That is when you want the count to be other than maximum value of 65535. So we're going to use up mode, and here we are assigning the value of 9 to the register, and this is just an example to understand the PWM generation better. And in case of PWM, TACCR0 helps us in finalizing the time period, that is the T on plus T off, and thus the frequency of our pulse width modulated signal. Since we don't want the duty cycle to be just 50%, which is something that we get in up mode using interrupt as we've seen in the previous video, so we also use CCR1 register, and this one helps us in determining the width of the pulse or the duty cycle. And here the value of this one is taken as 4. Now we know that there's a counter register which ticks with each clock pulse, and this counter goes on counting from 0 to TACCR0 value, which is 9 in this case, and then it resets because we are in the up mode. Now this is something that we already understand, but the new thing is that for PWM generation we won't be using interrupts. Instead, there is something called as output unit in each timer block, which gives an output signal, and the value of this signal, that is whether it will be set or reset, high or low, depends on both CCR0 and CCR1 value. So in this example, when the count starts from 0, the value of the out signal is high and it remains high till 4, that is CCR1 value, and then it goes low and it remains low till 9, that is CCR0 value. And then later on it again goes high from that value and stays high till CCR1 value, and the story goes on and we get an output signal which is our PWM signal. And in this case, as we can see, the duty cycle is 50%. So by varying the CCR1 count from 0 to CCR0 value, that is 9 in this case, you can practically get different duty cycles or different widths of your pulse. So that is how you get your PWM in your MSP430. Now the output or the PWM signal that we got previously depends on the output mode that is selected, and as we can see there are several of them. And this mode selection is done in TACCTL register, and we have used CCTL1, which is Capture Control Register 1, Capture Compare Control Register 1. And I have explained the details of this one in the previous video. So here in this particular register we've got out mode X bits which we can set to get a particular mode. And in case of PWM, we are only interested in modes that have 2 states possible. Thus, we can rule out all the other modes except for 2, 3, 6 and 7. out of which we've used mode 7, where we have already seen that the output resets when CCR1 value is reached and sets on CCR0. Now let's look at mode 7 in further detail. So we have our X and Y axis, as we know that the counter can count from 0 to 65535. So we have those two values set over here. But we'll also consider CCR0 value in this case because we're using the up mode. And for PWM generation, we'll be using CCR1 value as well. And pulse width modulated signal is obtained as output signal from the output unit, which in this case is out 7, which is nothing but output mode 7, the mode that we are using. So let's see how CCR0 and CCR1 helps us in getting this PWM signal. So first of all, the counter counts from 0 to CCR1, and the moment the counter reaches the CCR1, we see the output being reset, and the counter continues counting till CCR0, and the output continues to remain in reset state till CCR0. Then the timer resets or goes back to 0, and the output is set, and then it remains set till CCR1 value is reached again, and the story repeats, and we get a nice PWM signal. So we can clearly see that the width of this pulse can be changed by changing the CCR1 value, and it can range from 0 to CCR0 count, as we've seen previously, and the time period or frequency depends on CCR0 value. So now let's quickly see an equation which explains the relationship between the clock frequency and the PWM frequency. So that is given by FCLK divided by TACCR0. Now FCLK can be further divided by the divider. We are going to keep the divider as 1, so it'll be practically FCLK divided by TACCR0 value. So if you keep TACCR0 value to be high, then in that case you'll be dividing the clock frequency by a bigger number. That means the resulting PWM signal will have a lower frequency. That means it'll run pretty slowly. So the signal will be slower in duration. Now let's see an example. If the clock frequency is, let's say, 1 MHz and CCR0 is kept at 1000, then we'll get 1 kHz frequency for our PWM signal. Now next is the output pins from where we get the output signal. So this is a special functionality and not the GPIO or the general purpose one. So there are few pins, 11 to be precise, which are highlighted for getting the output signal, and we have used P1.6, and this is not selected randomly. This is for TA0.1, and in this case you can't, as I said, use any pin randomly, and you have to set the corresponding pin which is supposed to be used using port select command in the code, and in that command you'll have to select the timer functionality. So it's very simple thing to do in the code, and we've done that already in the code. Now we have written a code for generation of PWM signal, and we have fed the signal to P1.6, that is the green LED, and you can see the varying intensities for that particular LED for different duty cycles. So the PWM duty cycle in this case is 75%, and you can see that the LED is appearing quite bright, but it is not blinking, and that is because the PWM frequency is of 1 kHz, which is quite high than the frequency response of our eyes, which is 50 Hz, and that's why you will not be able to see the blinking, but rather you will see the intensity changing, and that's the whole advantage of this PWM. So now if I want to make the LED appear dimmer, then in that case I can just reduce the duty cycle and keep the frequency the same. So as you can see, for 2% it is appearing very dim, and this one has a duty cycle of 10%. So you can play around with the value of CCR1 register to get different duty cycles and thus the brightness levels. Now the code for this is, as always, available on my blog, and the blog link will be in the description below. Now let's see the PWM applications. So first of all is controlling the intensity of LED or any smart lighting system, as we've already seen in the LED example. Then you can generate audio signals using PWM from timer. Next, it is also used as poor man's DAC or digital to analog converter. And you would need a low pass filter to filter the resulting PWM signal to get an analog one in this case. And you can use an RC filter for the same. You can also control the speed and torque of motors. And you don't even need to use a low pass filter in this case because the system response is low pass anyway. Next, it can be used to drive an infrared LED for a remote control. So these are just few examples and not covering all the applications, obviously, just a few applications. And up next on the channel would be hopefully a video on small project implementation using PWM. So do watch out for that one. And there'll be another video on capture mode of timer, as we've already covered the compare mode. So we'll be covering the capture mode now. And do drop a like, comment and share the video. And don't forget to subscribe to the channel. And thanks for watching. I'll see you next time. Bye world.